Swayam Prabha. Digital India. Educated India.
Yes, we'll get started. So just before I start, there were questions here. I know there's a lot of material that is being squeezed into a few lectures. So I don't expect all of you to digest all of it, but hopefully this would be an exposure that will help you next time you see the same material, or even go back and go over the material. And also, a lot of the things you see, if you just look up online, they're not entirely reliable. So you could use this as a reference when you come across something. You can cross-check with how, there are also textbooks. We would give you some references for you to look at later. Okay, so let me get started. So there's a lot of stuff I still have to cover, but we'll see how much we managed to do today. So one thing we so far have been completely silent about is hash functions, and you would have seen hash functions as a big player in cryptography. A lot of things are called hash, even if they're not hash. So what are hash functions? Let's try to get some sense of it. So one thing about hash functions is that it maps long strings into short strings. Okay, and I call it a randomized mapping in the sense that it's not necessarily a lot of the hash functions that are used in practice are actually deterministic fixed functions, but we'll still think of them as having randomly generated or randomly picked from some family. And so for now, think of it as picking a function at random from a big family, and that's your hash function. And they show up with this randomization. They're useful in various places. You would have seen them in your data structure courses. There are hash tables. And the idea of hashing is that you are removing worst case effect. There could be some input that is bad for your algorithm, but you hash it so that that input doesn't create this bad effect on your algorithm. Like maybe there are multiple things that are going to go into the same cell in your hash table, but by this hashing, it will be only with low probability that will be a bad input for your data structure. Okay. But that's not quite the way in which it's used in cryptography, because if somebody we'll see some examples where the hash function is already out there. So the adversary can then maybe choose something that's bad for that hash function. It's not not that first the input comes and then you pick some hash function that will remove some bad effect, even though that's also a scenario at times, we'll see. But at a very high level, hash function gets used for integrity, okay? So authentication kind of purposes. And the way it gets used inside, so we already saw MAC last time. We'll be talking about digital signatures, which is a public key version of authentication today. And you could do them without a hash if you needed to, but the hash helps. The hash helps in the way it helps us in terms of efficiency. It can be used to take a long string and get a short string and then apply your MAC or digital signature on that short string. Okay, so that's the sense in which it will get used. And there are many requirements people have of hash functions, but maybe the most important one is collision resistance. And that means, collision resistance means you cannot find two inputs that hash to the same value, or it's hard to find such inputs. Also, we'll see different flavors of this collision resistance in a bit. Okay, and also some kind of unpredictability. So I talked about random oracles in the previous lecture. So hash functions are kind of heuristically taken to model a random oracle, or taken to be a random oracle, taken to implement a random oracle. So we'll see both kind of uses of hash function. Okay, so one thing that's almost always needed from a hash function is that it compresses. What I'm trying to write here is it takes n bit strings and outputs t bit strings, where t is something smaller than n. You can ignore the case there. Okay, so what does that look like? So that's each hash function, right? So in this example, the inputs, the n is 3, so it takes 3 bit strings and produces a 1 bit output. Okay, of course, it's not the kind of hashes we'll be interested in typically, but just as an example. But we'll have not just this one hash function, we'll have a family of hash functions. So each one is doing this thing. Take n bit inputs, give t bit outputs, and when you want to apply this hash, you typically pick one of these functions at random and use it. And you'll also say which function you are using, typically. Okay, so you could think of that as taking two inputs. One is a column index saying which function to use, and the other is a row index which is saying what is the input you want to feed into the hash function. So what is a function and what is the input to the function? You specify both those things, you get the output. So what do we want from this? So far I've not said anything about security properties, just kind of syntactic properties. So we want it to be efficient. We want to efficiently pick one of these hashes and and then evaluate it. Okay? So that's what is needed to find a value in a cell in this table. And sorry, I should also mention efficient sampling, right? This hash function family will have some representation, and you should be able to pick one of them, say uniformly at random, should be able to do it efficiently. And yeah, as I kept saying, the expectation from this hash function is that to get all these properties like collision resistance, what we really are hoping is that it behaves like a random function. So imagine this table had all the functions, okay, every possible function, and then you're picking one at random. That's kind of the effect we would like to have, but that's an inefficient function, because if this table had every function possible, then a representation of such a function is this entire column, but that's going to be really long when you have all possible inputs, right? There's some, think of it as some 128-bit input, and you have 2 to the 128 bits to specify, even if the hash function's output is a single bit. So having all functions there in your family is not going to be efficient, but that's kind of the effect you would like to have. Okay, when you pick your hash function at random from your small family, it should work like you have picked a function from the whole family, the whole all functions. Okay, and yeah, it should behave like random, and specifically it should avoid collisions. Okay, so it should be hard to find collisions. So let me show you. Before I go on and show you this formal definitions of various forms of collision resistance, this is not quite how it's used in practice. In practice, there are fixed functions, and these are some of the things you would. So SHA-3 and SHA-256 are standards that are still standing. The other ones are essentially all broken. They are not collision resistant or not collision resistant in certain senses. So SHA-1, MD5, MD4, they're all kind of old standards that are not to be used in many contexts. These are unkeyed, as in these are, well, SHA-3 there is a notion of you can have a key if you want, but in general, they are just a single function, fixed deterministic function. Yeah, never mind this security parameter knob, because that's something I didn't talk about so far. And this kind of single fixed function is not going to be collision resistant under the definitions we are going to see. Okay? Or at least if we formalize those definitions, then it's not going to be secure. We'll not really, yeah, we'll probably not get to that level of formalism. But then how do we justify what I'm going to talk about now versus how it's used in practice? Well, one thing is you could imagine that these standards, they were already picked at random from some family. And that's a reasonable assumption or a reasonable way of looking at it, because these things do have some randomly chosen values inside them, hard-coded into the standards. Things like IV, initialization vector, or round constants, they are kind of built into that function. So you could say, okay, those were randomly chosen, and that's how the world we are living in with those particular values, but in principle, they could have been chosen at random. Okay. All right, so collision resistance, there are many flavors of it. Okay, here is a little summary. We'll actually go through them line by line. They all have this flavor of an adversary, to be a secure hash function under any of these definitions. We want it to be hard for an efficient adversary to find a collision. What is a collision? Two inputs x and y, typically distinct. We'll require them to be distinct inputs x and y, which hash to the same value. Okay. Of course, so that's what a collision is, right? You want two inputs that hash to a same value. We are not specifying at this point what value. It's up to the. We'll see in these definitions when we put a restriction on that. Okay, so here's the first flavor of hash functions. These are combinatorial hash functions, meaning they're not, they're collision resistant information theoretically. They're not going to rely on the adversary being polynomial time. Okay, and here, but the experiment is kind of loaded against the adversary. The adversary has to first give me a pair x, y, and then I will pick a uniformly random hash function from my family. So this calligraphic H here is a hash function family, and this indicates that I'm drawing a hash function from the family. So the order of things is that first the adversary has to give me x, y, then I pick a hash function, and then I check if your x, y has a collision. Okay, and there you could imagine, right? It's kind of unfair on the adversary. It doesn't know what hash function you're going to pick, and it's very hard to get a collision if the function family is nice. Okay, so we do have such function families. So that's combinatorial hash functions. The next step is, okay, the adversary doesn't announce both x and y first. It only announces x. Then we pick the hash function and show it to the adversary. And then, so the stateful adversary, the adversary works in two stages. First it picks an x, then it gets back an h from you, and then it tries to find a y. Okay, this has a name. Doesn't matter what the name is. It's universal one-way hash functions for some historical reasons. But that's the next level of collision resistance. So the adversary has a little more control now. It can pick y after seeing this h. And here it's important that the adversary is computationally bounded, because if it were not, here the first x can just be a random x. And then it's guaranteed that with high probability when you pick an h, there will be collisions. Why will there be collisions? Because this is a compressing function. Okay, so it takes long inputs, gives you short outputs. So by pigeonhole principle, there will be a lot of things that go into the same bucket. And even if you spread it around as nicely as you can, by picking a random x, the adversary is guaranteed that with, on the average, right, there will be so many things that this x will collide with. And then it can use its unbounded computational power to find one such y. Okay, so here we will need computational limitation on the adversary for this thing to exist. The next flavor is, you can imagine, right? We give more control to the adversary. We first publish the hash function, and then the adversary gets to choose x and y. So this is a most standard form what you would refer to as collision-resistant hash functions. So this gives most power to the adversary. The adversary gets to see your hash function, and then it has to find a collision. All those things we talked about, SHA-256, this is the way you should think of it, because the adversary already knows that hash function, and now it's trying to find a collision. There's a flavor of weak collision resistance, where the adversary doesn't actually see the hash function, it only gets oracle access to the hash function. Okay, so we pick the hash function first, and the adversary gets to pick xy after that, but we don't show the h as we don't give it as an input to the adversary, we only give it oracle access, and that's its notation here. Okay, so yeah, so that's a little weaker than the standard collision-resistant hash functions. So the collision resistance is guaranteed only when the adversary doesn't see the hash function directly. The last two flavors here, they do not let the adversary pick x and y. Instead, we will pick x, and the adversary's job is to pick y. So the first one is the second pre-image resistant hash function, where we pick h and x, and the adversary will show it to the adversary, and the adversary has to pick y. And the last version is similar, but we don't show the adversary x itself. We only show it h of x. So there we are saying, look, so it's basically a one-way function. The question is of one-way function. We picked a function. It so happens that here the function is also sampled randomly from a family, and then we gave h of x, function is h, we gave h of x on a random x to the adversary and asked it to find some pre-image. Okay, so as opposed to the second pre-image, you could say this is just pre-image resistant hash. We're just asking for a pre-image, and so this is just a one-way function. The adversary should find it hard to find a pre-image of a given random of h of x on a random x. Okay, okay. So those are all the flavors of collision resistance. I'll now actually go into some of them. But before that, an important criterion about to even have some hope of having collision resistance, you need things to be big. So maybe this is a point I should have made more explicit in the previous lecture also. When we talked about things like discrete log being hard, if your group is too small, discrete log cannot be hard. Somebody could just brute force try. If your group has only a million elements, and you want to find the discrete log, you try g to the g to the 0, g to the 1, g to the 2, all the way to g to the million, and see if any of them matches the value that you're trying to find discrete log of. So it's important that we are talking about a humongous group, say with 2 to the 128 elements in them. That's what prevents a brute force attack in the case of a discrete log. Here, it's a little more than that. It's not just about the input length or the size of the hash function family. So clearly the input length, you want it to be big, the domain, right? But you also want the range to be big. Because if the range is too small, you can find a collision by accident, just by randomly trying. So it cannot be collision resistant if it is too short. The output of the hash is too small, short. Yeah, this would be the attack. Forget which flavor of collision resistance we are asking for. Just pick x, y at random. Try, just output it. And for any h of x equal to h of y happens with a non-negligible probability if h of x and h of y come from a small family. Okay. So we need large hash outputs. On the other hand, in practice, the whole point of using this hash function often is to take your input and make it much shorter, right? So that you can then sign it or authenticate it using a MAC. So you want the output to be as short as possible for efficiency purposes. But there is this tension. If it's too short, it won't be collision resistant. And then whatever you're trying to do will not be secure. So there is a sweet spot as to how small you can make this hash function. And one important consideration there is what's called the birthday bound or the birthday attack, which is a slightly non-obvious way of coming across collisions. Okay? And this is for this flavor where the adversary has the most power, the collision resistant hash function. So CRHF stands for collision resistant hash function, where the adversary first gets H, and then it is trying to come with a pair XY such that h of x equal to h of y. It can do a little better, actually significantly better than a naive attack. So let me say what that thing is. So actually, let me maybe just explain what this birthday word stands for. So this is kind of an experiment, right? You just go into a classroom like this and you ask everyone what's their birthday. So there are, we have some, 50 students here or something. And you would think, okay, there are 365 days in a year. What is the chance that two of you will have the same birthday? It should be small. The point is, if I ask you, how many of you is there anyone who was born on Jan 1st? Well, then I probably don't expect, anybody here, unless it's a big enough classroom. I don't expect to see any student with that particular date, birthday, or let alone two students, right? But if all I'm interested in is, are there two students who have the same birthday, some same birthday, then with about something like 25 students, you already have a good chance of finding a collision. So you don't need 365, you kind of roughly need square root of that before you start finding collisions. Okay, that's why the name birthday bound is, you'll start finding collisions in a small group beyond, in terms of birthdays, before you would have expected. So the attack is that, right? We don't care which value h of x should be. We only need a pair x and y such that h of x equals h of y. It could be any value. So you pick a reasonable number of people, square root, size of the range, and roughly there are n square pairs there, right? So n says the size of the range. There are n square pairs there, and in a very rough sense, so you picked, I should say, the range is something else. Let's say size is t, and you picked n people, once, and n is say square root t. There are, in a group of n people, there are about n square pairs, xy pairs. And you would, if there n is square root t, you have about n pairs, and each of them has kind of 1 by n probability of being a collision. Why is it 1 by n probability of being a collision? If I pick x, h of x is some value, and y can have n possible values. One of them is going to collide with this x. So you could think of it as, for any pair, there's about 1 by n probability of a collision. So once I have this, roughly n pairs, you have about, good probability that, or a good expectation that you would find a collision. Okay? So roughly, so the attack goes along those lines. You pick a number of people which is not as big as the range, but square root the size of the range, and then you look for any pair there that has a collision. So what birthday attack does is effectively it halves the security that you're getting from a hash. You would have thought, so if it is one of the other flavors of collision resistance, like this universal one-way hash function, where the adversary has to first commit to an x, then we pick the hash function, and then it's trying to find a y. Well, then it has to collect enough y's, this 2 to the 64 y's, before it can hope to see a collision by accident. But so it has, in some sense, 64 bits of security, the universal one-way hash function with a 64-bit output, at least against a brute force attack. But with and there is no birthday attack possible there, right? It's already picked x, and then it has to pick a y. But in CRHF, it only gives you 32 bits of security. Okay, so that's an important consideration about picking the hash length. The brute force attack is not as naive as you would expect. Okay, so now going back to the flavors of hashing, the first one was a combinatorial hashing, and universal hashing is a particularly nice form of that. So this was a requirement, right? The adversary should find a collision with negligible probability. So first it finds xy, picks xy, then we pick h. This universal hashing is a little even kind of nicer structure to it. It asks for some more smooth properties. And those the properties are uniform and pairwise independent. So the two here, two universal stands for, the 2 stands for pairwise independence. So 2 universal is just a short form for these two properties. So what are these two properties? Uniform just means if I pick any x, fix any x, and I pick a hash function at random, the output will be uniformly random. Okay? In terms of the table we had in the beginning, picking an x is picking a row, picking an h at random is to look at the entire row, and in the entire row you will find every possible value in the range equal number of times. Okay? So that's this is a notation for that, saying that for every possible input x and every possible output value z, the probability that hx will be equal to that particular z is 1 over the size of the range. So the range is called capital Z here. Okay? So it's just saying that picking a random h will result in a random output, uniformly random. The pairwise, so this is an example of that, right? For every, so this is a tiny example, of course. There are 4 functions here. The domain has 3 elements. The range has only 2 elements, 0 and 1. And you look at any row here, you see equal number of zeros and ones. Okay, so that is uniform. That's a uniformity property. The pairwise independence says that I look at, for any pair xy, any distinct inputs xy, I tell you what h of x is. So I pick an h at random, tell you what h of x is. It tells you nothing about h of y. Okay? Another way to say that is, if you look at the pair x comma y, hx comma hy, that is uniformly random over pairs of values. Okay, so let's see that here. So these are the pairs of values of output w and z. And we are saying for any w and z, the probability that both of this happens, h of x equals w and h of y equals z, will be exactly 1 by z square. Okay, or it'll be equal to there's the independence saying that these two events are independent. Their probability is the product of their probabilities, which is each of them is 1 by z, so it'll be 1 by z square. Okay, so looking at this example, I take 2 pairs, 2 x and y, say 1 and 2. What we are looking for is that the pair of values hx and hy, so h1 and h2, as a pair is uniformly distributed over all all pairs of bits. So there are 4 pairs of bits, right? 0, 0, 0, 1, 1, 0, 1, 1. Each of them should occur equal number of times, and indeed each of them occurs once. If you look at the pairs here, 0, 1 occurs once, 1, 0 occurs once, 0, 0 occurs once, 1, 1 occurs once. That's for that particular pair of inputs. You can look at another one and you will see the same thing, and you can look at this one, 0 and 2, and you would see the same thing. Okay, so this is a tiny example of something that's 2 universal. It's a 2 universal hash function family. Those 4 functions form such a family. Okay, and with these 2 properties, we can calculate the collision, the advantage or the success probability of the adversary in this experiment. No matter what x and y the adversary gives, right? But 2 distinct x and y. So for all x not equal to y, we can compute the probability of the collision happening. Well, what is that probability? It's basically there are in this case, right? There are 1 by 2 square, or there are 2 square possibilities, or there are z square possibilities of which in exactly z of them they are equal. So here there are 4 possibilities, and exactly in 2 of them they will be equal. So they will be equal to 0 in one, they will be equal to 1 in another case, right? So it will be z, size of z upon size of z square, which is size of 1 over size of z. That is the probability of collision. And that would be a tiny probability of collision. So here there is no birthday attack to worry about. So if you just want 64 bits of security, you just need an output length of size of 64, right? So you'll get 1 by 2 to the 64 as a probability of the adversary winning this game. Yeah, so we need this size of z to be large. Super polynomial is a technical term for large. This was 2 universal. You can ask for k universal, which is instead of pairwise independence, you will say there should be k-way independence. So for any k pairs of inputs, distinct inputs, and k possible output values, the probability that these inputs take exactly those outputs should be 1 by z to the power k. That's k universal. And there are several constructions. There are nice constructions. We have gone through them, but since we don't have time, we'll not do that here. Yeah, so just, they exist, right? There are combinatorial hash functions. And we'll have some use for this shortly. How about, I'm skipping some of the other flavors and just jumping to collision-resistant hash function, which is the most popular one. What do we know about constructing them? Well, we know we need computational hardness assumptions. Theoretically, they can be built from a few different assumptions, but one way of building them is from what I call claw-free pairs of permutations. So it doesn't matter what they are. The important thing is that in turn can be based on hardness of a variety of problems. So discrete log that we talked about. We will see actually a CRHF based on discrete log. Or factoring, so hardness of factoring, and some hard problems from something called lattice-based cryptography. We have not talked about it today, but that's another flavor of, flavor of mathematical structures from which you'll get hard problems useful in cryptography. Okay, but these are not used in practice as much. As a general purpose hash function because they are expensive. They have some further nice properties that will be used in some applications, but not in the ones we are going to talk about because they are expensive. And but yeah, still I want to kind of show you that one of those constructions, and that is collision-resistant hash function from discrete log. Okay. So we need a group where the discrete log assumption is holds or is assumed to hold. We further need the group to be of prime order. So the number of elements is prime in the group. And there are such groups, candidates. ZQ star is one such group for a prime Q. And here is the hash function, all of it, right? So there are some 2 elements that, so the hash function is described by 2 elements from the group, 2 non-identity elements from the group. So G1, G2 not equal to 1, right? So the family contains all such functions, which are for all possible pairs of G1, G2 not equal to 1. In a prime order group, any element other than the identity is actually a generator. Prime order groups are cyclic, and every element is a generator other than the identity element. Okay, it doesn't matter, that's how it is. And the hash function is simply this. So you take what is the input? The input is a pair of integers. Okay, but integers which are also in this range, the order of the group. So 1, 2, 3 up to the order of the group. Okay, so x1 and x2 there are equal number of them as there are group elements. x1 there are equal number, x2 there are equal number. So this is as good as, it's almost like 2 group elements, but they are represented as integers. And what's the output? It's a single group element. So you take two blocks, output one block. The input blocks are interpreted as integers. The output block is derived as a group element. And how do you compute this output? Simply this, g1 to the power x1 times g2 to the power x2. Okay? And I'll show you a very quick proof that this is collision resistant under the discrete log assumption. So what does a collision look like? Suppose the adversary manages to find a collision. So there's going to be a reduction. If there is an adversary who finds a collision, I'll turn that adversary into an adversary for the discrete log assumption. I'll use that adversary to find discrete log of what? I'll do something like discrete log of g2 to the base g1. Okay, that's what I'll use this adversary to compute. Okay, suppose the adversary gave us a collision x1, x2 distinct such that g to the power whatever g1 to the power x1, g2 to the power x2 equals g1 to the power y1 times g2 to the power y2. Now, if if these hash values are equal, and suppose x1 not equal to y1. Okay, so when I say x1, x2 not equal to y1, y2, either x1 not equal to y1 or x2 not equal to y2. Right? So suppose x1 not equal to y1, well then you kind of also get that x2 not equal to y2. Why? Because if x2 were equal to y2 and this holds, then x1 will have to be equal to x2. Okay? g1 to the power x1 will have to be equal to g1 to the power x2. In group and identities you can do cancellations. So you have that, x1 both, x1 not equal to y1 and x2 not equal to y2. And I can write down, so this expression that I have here, what I showed you earlier, g1 to the x1, or what I said earlier, g1 to the x1, g2 to the x2 equals g1 to the y1, g2 to the y2. You bring things under g1 on one side, on the right hand side, things over with g2 on the left hand side. You'll be left with g2 to the power x2 divided by g2 to the power y2 equals g1 to the power y1 divided by g1 to the power x1, okay, which I am rewriting as, so g2 to the power x2 minus y2 equals g1 to the power x1 minus y1. Or maybe it was y1 minus x1. Okay, I think it should be y1 minus x1. Okay, but you can write an equation essentially of this form, and you can divide in the exponent. You can take the root. So what does that mean? Well, the x2 minus y2 is a number modulo q. The exponents are numbers modulo the order of the group. So x2 minus y2 is a number modulo q. It has a multiplicative inverse. Okay, all the arithmetic in the exponents are happening modulo q. So dividing by x2 minus y2 makes sense. It is basically multiplying by some other number which is a multiplicative inverse of x2 minus y2, and x2 minus y2 has a multiplicative inverse because x2 is not equal to y2. Then I have this expression g2 equals g1 to the power something, and this something is something I can compute, x1 minus y1 divided by x2 minus y2, everything modulo q. So by giving me this collision, the adversary has given me the discrete log of g2 to the base g1. Okay. So if there were an adversary who could do that with significant probability, then they will be breaking the discrete log assumption. So so that's why there's a secure hash function under the discrete log assumption. And this is a nice hash function. It took two group elements or two blocks and gave me one block output. Right? It's reduces the size by half. Okay, so that's one. It reduces size by half. That's not good enough, right? If I have a gigabyte of data that I'm trying to hash, I don't want half a gigabyte of data. I want some 128 bits or something. Okay. So I want to take this huge data and I want to get a very short output. So how can I do that? Okay, and that is this idea of a full domain hash. The hash we said its output has to be 128 bit. Its input, we don't want it to be just, say, 256 bits. We want the input to be as long as you want. It should be arbitrarily long. Okay. So let's see, if we can do that. So the CRHF we saw in the previous slide doesn't do that. So let me show you how to do that. But first I'll do that for a fixed domain. So you tell me you are interested in hashing 1 gigabyte inputs into 128 bit. Okay, so I'll give you a hash algorithm which only works for 1 gigabyte data. It doesn't work for 2 gigabyte data. So, but it's still extending the domain. It's not full domain yet. So that's what this domain extension means. So the input domain of the hash function, I want to now change it to something bigger, say 1 gigabyte long strings. So let's see how we will do it. And what are we given? We are given this little thing which takes 2 blocks and produces 1 block. And we want something which takes 1 gigabyte and produces 1 block. Block being something like 128 bits. How do I do that? I use something called a Merkle tree. Okay, so it's the same Merkle that we saw earlier with Diffie and Hellman, and he had this construction as part of some signature construction, but it's a very versatile thing and can be used here. And yeah, so you're given this hash function which goes from 2k bits to k bits. You make a tree out of that. Okay, so this tree has so it's a binary tree. At each node, imagine a hash function sitting that takes 2 blocks and produces 1 block output. Okay, so at the bottom you have 2 blocks coming into each node, each leaf, and then for this just a binary tree, and at the output will be a single block. Right. So this is what a Merkle tree looks like. So in this particular example, there are 8 blocks of input, and using a tree of depth 3, we can make it hash it into 1 block output. So is this clear what the hash function is doing? So each leaf takes 2 blocks of input. So you can, if you want to, here in this example, I wanted 8 blocks as input, so I had depth 3. If you wanted 16 blocks, you will have depth 4 and so forth. Right? But you fix that depth. You tell me ahead of time what it is. And even if it's like a billion, you'll have basically whatever is the number of blocks that you're interested in, you'll have essentially that many nodes here, -1. Okay. All right. I said, I made it look like a balanced binary tree. It doesn't have to be a balanced binary tree. It can be any binary tree. The input-output sizes just need to be consistent. It could even be not binary. If I had a hash function that was, say, compressing by 3, it would be natural to use a ternary tree. Okay, and at every node, it's so to describe this new hash function, I just need to describe what a single hash function from the original family, and I'll need to use that everywhere. Right? Every node will use the same hash function. So how do I know that this is going to be collision resistant? So let's actually see this. Suppose suppose the adversary manages to find a collision. It finds 2 8-bit blocks that hash to the same value. I'm claiming that adversary, I can use that adversary to find a collision in the original hash function which takes 2 blocks and produces a 1 block output. How? Yeah, so suppose there's a collision, x1 to xn and y1 to yn. So this x1 to x8 and y1 to y8 both hash to the same output value. I'm going to find a collision for the basic hash, right, a single node. Here's what I'll do. I'll write down this entire computation in this tree, like at in every edge I write down the value of that block. And so initially, so I draw a front line or a cut in this tree. And I keep 2 copies of this tree, one evaluating the hash with x1 to x8 and another with y1 to y8. Now, x1 to x8 and y1 to y8 are different, right? So they are, the invariant I'm going to maintain is that in these two copies, if you look at the entire front line, they look different. Okay. So initially I have that invariant. Then I try moving my front line up. What could happen? Well, one possibility is that I found a collision, meaning now this edge, the block in this edge became the same in the x computation and the y computation. Then I'm done. Then I have, then I'm, okay, not quite done, but if they have become identical, but these were already identical, then I still have the invariant that in this entire path there is still some difference between in this. Let me see. Maybe So afraid I don't have a good way to draw, so I'll just try to speak through this. So the invariant I'm maintaining is that in this entire front line, in the x computation and the y computation, there is some difference, right? All the blocks, if you look at all the blocks, they are not the same. Initially I had that. Now suppose I moved this front line up and that invariant disappeared, okay, meaning they became equal. Well, what does that mean? That would mean that all of these are the same for the x computation and the y computation. So this should have been different because I knew that they were different earlier. So the difference should have been here. And further, this is the same in the x computation and the y computation because that's why the invariant disappeared, right? So now I have found a collision because these were different in the x computation and the y computation, and these are the same. So this x1, x2 and y1, y2 are different, but h of x1, x2 and h of y1, y2 are equal. Okay, so when the invariant disappears, I would find a collision. But maybe the invariant doesn't disappear. Well, then I keep going. Okay? And at each step, it's the same argument. So I keep moving my front line. At the end, the invariant does disappear, right? Because the only thing in this front line is this one edge, and there is a collision that the district gives, so they are equal. So somewhere, starting with the invariant holding to the invariant not holding, there was one step where it went from holding to not holding, and that one step will give me in a single node collision. Yeah, but I'll see what this collision. Okay, so that's good. That lets me build collision resistant hash functions which take very long inputs. Unfortunately, it's still not full domain hash because I need to tell what that length is ahead of that. I need a fixed input length to design my tree. Now, if I want to have a full domain hash, all I do is that I would say, okay, I will dynamically decide what the, when I see the input, I decide what the structure of this Merkle hash is. But the output is not just the output from the Merkle hash. I'll further hash it with a block which encodes the length of the message. Okay? So my final hash is this one. How does this help? Well, the previous argument only helped me find show that working with a particular fixed length, I get collision resistance. Now, if you give me a collision, there are two possibilities up front. Either you give me two strings which have the same length, in which case I can use the previous argument and find a collision, or they have different lengths. Well, if they have different lengths, then I already have a collision here, because this block will be different for the two inputs, and the output is the same. So I can get a collision at the root. So this is a very standard approach to constructing hash functions. If you look inside things like SHA-256, this is what's going on. It's called Merkle-Damgard iterated hash function. There, the tree is not in the form of a balanced binary tree; it's in the form of a chain, but still the same argument. Okay, so any questions on CRHF so far. So I'm done with just describing the two things I wanted to about hash functions, construction of hash functions. We saw two universal hash function, we didn't see any construction. We saw Colson-Russell hash function, we saw construction, right, using discrete log and this Merkle-Damgard iterated hash function. Okay, now I want to move on to using these hash functions.